No, this time. It's a great pleasure to welcome Claudia de Rham from Imperial College. She tells me she hasn't been to Dublin, and unfortunately this virtual visit won't get her to see very much of Dublin. So we'll have to have you visit again, Claudia. Claudia's going to tell us about positivity with gravity. So welcome, Claudia. Thank you for agreeing to give this lecture.
Thank you very much, and thank you for the invitation. It's nice to be virtually in Dublin, at least, and I get to see a few of the offices. Yeah, so I'll be talking about positivity with gravity. And first of all, I'd like to thank my collaborators. I'll be discussing about some combination of various papers, all under the theme of trying to apply positivity bounds within the context of gravity and what it means in terms of constraining low-energy effective field theories. So I'm a cosmologist, and the point of view I'll be taking often is from the point of view of effective field theories for cosmology, but really all the methods that are being developed, they are applicable for any type of low-energy effective field theory. So the question the whole community is asking ourselves is to understand what is the communication between the low energy framework that we're experiencing and that we're observing, and with an ultimate completion of quantum gravity and everything. And ideally, you would start with your favorite model for quantum gravity and then cascade your way down to a representation of a model at low energy. So hopefully get GR plus some the standard model fields, plus some extra maybe light degrees of freedom and possibly dark matter and everything that describes the universe as we see it at low energy. Unfortunately, this communication from the high energy physics and the low energy one is not as simple as that. And from the low energy effective field theory point of view, the framework is much more of a landscape of various types of models that people have come up with in describing the low energy world that we experience. And one of the aim of the game is to try to segregate between these different types of low energy effective field theories and understand whether they're consistent and whether they could be ultimately embedded back within a consistent high energy completion. So when we try to segregate between different types of effective field theories, the best thing we should do really is to simply look at different signatures of our model and then compare with the real world, look at different observations, different experiments, and then really converge in a particular model, hopefully in the description of whatever phenomenon we're interested in. And that is doing very well. As an example, which I'm not going to go through today, but just in the plethora of models that came up for the description of dark energy, a lot of those models were leading to a speed of gravitational waves that were departing from that of light. And just from the observation of the gravitational waves with optical counterpart, a large portion of these models could simply be ruled out. So comparing with the real world is, of course, the number one way science will evolve. But in parallel, there's very economical ways to constrain our different type of effective field theories. And I'll quickly mention what I mean by theoretical constraints, and then I'll go really into a different type of still theoretical constraint, but I'll separate them both, which I'll call high energy completion. So in terms of theoretical constraints we can implement in our low energy models, I really have in mind something which doesn't require any knowledge of how our model will ultimately be completed at high energy. So really, this type of constraints goes under the name of whether they are healthy, whether they're really physical, whether we are using them in the regime of validity where they are applicable. These are all low energy theoretical constraints we can ask ourselves, and that allows us to segregate between different types of models. One of them, for instance, we may be inclined in including is that related to causality, or that related to subluminality. And I'll just mention it now because I'll go back to it later on. But in many low energy effective field theories that we may have for gravity, but it can be also for light or for any other thing you may be interested in, we may end up with the speed, the low energy speed of, let's say, gravitational waves, which is not luminal on backgrounds that spontaneously break Lorentz invariance. So, for instance, the speed of gravitational waves will depart from luminality around a black hole in the effective field theory for gravity. And one of the directions we as a community have been following in the past decade or so often is to constrain our models so as to ensure that the speed always remains subluminal. And the reason for that is because we all know, we all learn that any amount of superluminality is directly related to causality violation. Now, it doesn't matter too much how small the level of superluminality is. It's enough to have a small amount of it so that you can ultimately ride on this small amount of superluminality and construct a framework where you can have as much departure outside your icon as you wish, and then boost yourself into a different frame and start seeing things which go backwards in time. So typically we constrain our low energy effective field theories in a way to ensure that we prevent the presence of any level of superluminality. Now, the reason I'm introducing that is because particularly in the gravitational context, the relation between superluminality and causality violation is actually not as straightforward as we typically imagine. And actually, it's not straightforward even for standard field theories. But with gravity, yeah.
Can I interrupt? How can one say that? Because one needs the causal structure before talking about a causality. The value of delta C, I mean, whether it violates causality, it depends on the causal structure of space-time.
Yes. So what I mean by that?
You don't know.
Very good. The one is in comparison to, let me just say, a pro-particle, let me take light in this context as I can, the speed of light at infinite frequency. And that will be considered as the front velocity. And that is what determines my causal structure. Yeah. So this one is not innocent, it is really the infinite frequency speed of, for instance, light or any other particle. Yeah.
Measurement of delta C is local measurements, so far as I know. Okay. Whereas causal structure, causality violation, the experiments I know are global. I mean,
exactly.
One can compare the two.
Yeah. So I entirely agree with you. I entirely agree with you. And I will discuss a little bit about that. And indeed, this all has to be taken into account in really determining whether or not there's a violation of causality. The reason I'm raising that concern in here is that often we are lazy. We as myself are lazy, and we may have some low energy effective field theories where we simply compute the local effective speed at low energy, for instance, of gravitational waves. And if we see it as being every so slightly superluminal, we simply throw that whole parameter space away, because we have learned, we kind of have a Pavlov reflex that any amount of superluminality is then related to causality violation. And I entirely agree with you, the connection with the two of them is not local, and it is much more subtle than that. In the case of, in reality, if you have a spacetime which is asymptotically flat, the relation between superluminal low energy speed and causality violation in a lot of the time is actually straightforward. And you can see this is just textbook derivation of that statement. If you think of the speed of light at low energy as it goes through a medium, it can be characterized by the refractive index. And so the speed would be related to the refractive index of the medium. Now, the imaginary part of this refractive index is related to the scattering amplitude, and unitarity tells us that the imaginary part of the amplitude of the refractive index has to be positive at any frequency, including at arbitrary high frequency. And it's really at infinite frequency where this is really all the relevant information comes from. Now, in the statement of causality, really it tells you that you want to ensure that there's no causal support outside the light cone. And so that is related to a notion of analyticity of your green function in some part of the complex plane. And that's also related to analyticity of your scattering amplitude in the energy plane, if you want, in an energy square plane. And this analyticity allows you to relate the refractive index at low frequency to that at infinite frequency, related to the integral of the imaginary part of the refractive index along what we'll call the branch cut, or along the whole spectrum of frequency. And so if you really really require unitarity for arbitrary high frequency, so you want the theory to remain meaningful, not the theory, but you want the embedding to remain meaningful up to arbitrary high frequency, that directly tells you that the velocity at small frequencies has to be smaller than the velocity at high frequencies. And the speed of light at infinite frequencies, or the speed at infinite frequency, is really what we call the front velocity, and that is the speed of propagation of information. And this is what has to be liminal to ensure causality, because this is what is setting up the causal structure. So this is in a standard, this is really just textbook standard arguments that you can work out for light. And that's really what we learn, that the phase velocity at low frequency has to be subluminal, because violation of that would be related to causality violation, or even worse, unitarity violation. I mean, it's up to you to decide which is worse, actually, but a violation of some of those assumptions. But embedded in the requirement that the low frequency speed has to remain subluminal to ensure causality is, of course, some requirement of how things have to behave up to infinite frequency. So this is embedded in the fact that we integrate all the way up to infinity. Otherwise, we have absolutely nothing to say. And so that's why the notion of what the speed of any species at low frequency is doing, whether luminal or subliminal, and the consistency of that is not really a theoretical constraints we can impose in the absolute low energy, is also related to how the model will ultimately be completed at high energy. And in a lot of the low energy effective field theories that we're working with, here I'm taking the opposite approach, where we having more phenomenological approach, we're building up various types of models that are hopefully good description for what the universe or nature is doing. And then we're trying to understand whether those low energy effective field theory will ultimately be embeddable within a consistent high energy completion. And the word consistent is loaded. I'll explain what I mean by consistent and how it comes into play. But once we have this, what I'll argue is a consistent high energy completion, or what we can argue a model that will in principle be embeddable in a consistent high energy completion, then we'll like to ask ourselves how the notion of causality manifests itself at low energy without needing to go back to what's happening at very high energy.
Can I interrupt, please?
Sure.
Yeah. From what I know, what you wrote down looks like the forward dispersion relation. The equation you wrote for the integral of this one, this looks like the forward dispersion relation, which is proved in relativistic quantum field theory when there are no massless particles. Okay? Yeah. Or if you can say in optics, the signals come after the you receive the signal. Actual effect comes after the signal is received. So you get an analyticity from the Fourier.
Exactly.
Okay.
Exactly.
Now, I have a problem with this, because this is a massless theory, and there are very extremely complicated infrared effects in these problems. Okay? So at a low energies, and recent, in fact, for a long time, it is known that even QED breaks Lorentz invariance, okay, because of the infrared effects and the existence of many supersolution sectors. So people are, from what I understand, the analyticity properties that one postulates are not correct when you have massless particles. For example, here gravitons.
Yeah, I will talk about that. So I will precisely talk about that, and you're going exactly in the direction I'm headed to. So for photons, actually, I entirely agree that there's because of the massless particle, there's some small breaking of analyticity due to the massless pole. For the photon, it's not going to impinge on this type of relation. And I can explain why. For the graviton, that's precisely the point. The non-analyticity, which arises from the masslessness of the graviton, is precisely affecting this type of relation in such a way that there's not such a clear one-to-one correspondence between causality violation and subluminality at low energy, because this relation stopped being it's not quite at that relation, but precisely because of the non-analytic structure of the massless pole. Yeah.
But you are also working in a flat space background, which is probably an additional approximation that is forcing.
Yeah, so that is subtle if you want really to go into cosmology, for instance, where you're not asymptotically flat, and that's going to be an issue. There are contexts where we still can make this connection, for instance, around black holes, where you have part of the curvature, but still, if you're very far away, the curvature is still under control, is still perturbative, and that the fact that you're in a curved background is the spontaneous breaking of Lorentz invariance, which is going to mean that the speed is not exactly luminal, but it doesn't. The asymptotic are still flat, and so you can still compare with what you would have expected from a Lorentz invariant theory in a Lorentz invariant background. Yeah. The question of how to deal with those requirements for cosmology is much more subtle, so much so that I have very little to say. It's very much a direction in progress, but there's a lot more to be done in that direction. Okay, so but even I think it's very good because we identified most of the issues that some of them I'll try to say something about, and some of them I'll just tell you honestly that it's too hard for me to even deal with it at the moment. But just to put things a little bit in context into what we like to do, we may have a description for what's going on, let's just say in particle physics or in any phenomenology that you're interested in. And then you may say, well, this model may or may not have some high energy completion. Maybe it's embeddable in string theory. Maybe it's not string theory, but it's another type of high energy completion. But a priori, one we haven't even invented yet. But a priori, it's very hard to make this contact between the low energy effective field theory to the high energy effective field theory. Or the ultimate theory of everything, particularly if at low energy everything seems to be consistent in that it preserves perturbative unitarity, it's consistent with all the observations and experiments that we can allow for ourselves, so it seems like it's a relatively good model of what's going on. But for some of those models, we do know, and we have ways to tell when they will never be able to enjoy a standard high energy completion. And it's not subtle in the sense that we really try to tune our parameters such that we have a parameter in the low energy effective field theory and we tune it to a particular value, which we're not allowed to. But if it was ever so slightly away from it, we will be okay. It's not subtle. It's really black and white sometimes. And so it may seem a little bit puzzling of why you have this communication between high energy physics, maybe physics at the Planck scale or the string scale, to the low energy world, when you think you should be having just a decoupling of scales between the two. But it's actually precisely in the requirement of causality, which manifests itself under the notion of analyticity, at least in at some level, that we can still have some of the elements that happens at low energy impose some constraints on what is allowed from a low energy effective field theory point of view. Now, some of what I'm saying is probably sounds quite familiar, and there's different directions, of course, people have been following in the community in really trying to see how different types of low energy effective field theory could or not be ultimately embedded within string theory or within consistent high energy completion. So swampland is probably the one most people have heard of. I don't quite know myself where to put the swampland conjecture within the scales of assumptions we're imposing ourselves at high energy. So this is really just a cartoon picture, but it's kind of slightly disconnected to the type of considerations that we're having because it's a little bit more conjectural. Well, what we have in mind is really imposing the condition that our high energy completion, no matter what it is, should be unitary. So the S matrix should be unitary. It should be local in the sense that it satisfies the Froissart bound. And I know some of you are going to tell me that for massless graviton, we don't know that this has to be the case, and I agree, but I'm still going to impose on myself that level of locality such that the Froissart bound is satisfied. Going to impose Poincaré invariance so that we have crossing symmetry, and we can impose on ourselves a notion of causality so that which will manifest itself in the requirement of analyticity. And if you're not happy between the connection between causality and analyticity, then I agree with you and take what I'm saying as a requirement of analyticity. So that even then, there's different directions people have been following, but they really all rely on similar type of assumptions and similar type of procedures. A lot of the time is whether how precisely it gets implemented at the end of the day. I'm going to be following a positivity bound direction, which is all analytic. In parallel, people have been following some very complementary direction, which you may have heard under the name of S matrix bootstrap, which is more numerical, and both have their strength in some sense. So this is roughly the level at which I'm going to be working at. And now in terms of these assumptions, I want to see how requiring all of those for the high energy completion of my theory without having any knowledge of what the field constant, what the field content is at high energy, this is still going to allow me to impose constraints at low energy. So for that, let me just start with a scalar, massive scalar field. So there's none of some of the issues we discussed about. Let me imagine I have a massive scalar field, low energy effective field theory. I have a theory for it. And at low energy, I can compute some 2-to-2 scattering amplitude. And at low energy, I can use the theory to compute this amplitude and trust my result. So there'll be a region in my complex, S is a center of mass energy square. So there'll be some region in my complex energy square plane where the amplitude I compute using my low energy effective field theory will be valid and will reproduce something which is closely related to what should be doing. Then beyond this regime of validity, I can no longer use my low energy effective field theory to compute the amplitude, but the amplitude still exists, and the amplitude still exists up to infinite energy if I want to. I simply need to include new layers of physics to be able to compute it explicitly and describing what's going on, which I'm not going to be able to do. So I'm going to remain agnostic on what new layers of physics remain, and you may need to include an infinite number of layers of physics all the way to ultimate high energy completion of everything, which I certainly don't know what it is. And I certainly am not able to compute the amplitude outside the regime of validity of my low energy effective field theory. But the amplitude still exists outside of it, and I'm simply going to require that it remains causal, for instance. And the requirement of causality tells us that the amplitude itself has to remain analytic in the complex energy square plane, aside from the branch cuts and the poles that exist on the real axis. And it's precisely this notion of analyticity that will allow me to communicate some of the requirement I impose at high energy to some constraints within the low energy effective field theory, the regime of validity of the low energy EFT. Now, what we really want is a notion of unitarity for the amplitude up to infinitely high energy. And that tells us that the imaginary part of the amplitude, this is for a massive scalar field theory, otherwise the discontinuity of the amplitude along the branch cut has to be positive. This is the requirement of analyticity, of unitarity. And then from Lorentz invariance, Poincare invariance, I also have crossing symmetry, which at least for scalar field theory tells me that I also have positivity of the imaginary part of the amplitude along the negative side of the branch cut. So this is really what I'm gonna require, and I want this to be true all the way up to infinite energy square, if you will. Now, in the requirement of causality or that of analyticity, if I only have a non-analytic structure which is along the real axis in the branch cuts and the poles on the real axis, then I can relate what's going on at low energy with a Cauchy integration over an arc which is at arbitrary high energy. And so now imposing locality, which I want to manifest it under the Froissart bound, tells me that the amplitude can grow, but it shouldn't grow faster than S squared. This is the Froissart bound that I will impose on myself, and that's true. Martin has shown that this was true for massive particles. For massless particle, this is more debatable, but I'm still gonna assume the presence of the Froissart bound. So if you want, just take the Froissart bound as one of my assumptions. If the Froissart bound is satisfied, then I can send this arc to infinity and the contribution from it will go to 0. And so I can directly relate, in this case, it's the double derivative of the amplitude, the double derivative so that it's suppressed by sufficient power of S, the double derivative of the amplitude to the integration of the imaginary part of the amplitude along the branch cut, which we know has to be positive. And so that tells me no matter what this integral is, the whole result has to be positive. And so consistency of the low energy EFT at the very least requires me that the second derivative of the amplitude at low energy has to be positive definite.
Could I ask a question?
Sure.
Where do you get the formula for
Sorry, I couldn't hear the last part of the sentence.
I think your sound is gone again, Charles. I think his sound is gone, so we can restore. He can ask in a minute again, but we should probably move on because it's not going to work.
I think he meant where does this formula comes from? A double prime.
The Froissart bound or this one here? This is just a Cauchy integration formula, this one.
Okay, thank you.
Yeah, this is just my Cauchy integration formula that follows from analyticity. So the poles are the poles on the real axis, and I can compute those. They are in the regime of validity of my EFTs. It's just the poles coming from the fact that I have massive particles in my low energy EFT. So they're present there. And then the low energy EFT may be valid all the way up to some cutoff. I don't know where it is exactly, but that's whatever is there, and whatever poles we come in from the new layers of physics is hidden in that branch cut. Whatever they are, they have to give a positive contribution to the imaginary part of the amplitude. But the causality or analyticity tells me that I can perform this Cauchy integration formula. So all of this is exactly the same procedure as what was done in the optical case earlier and was known for half a century at least. Okay, so in the case of, this is the case of a massive low spin theory, EFT, there's a direct connection between the assumptions that we're imposing on ourselves for the high energy completion. No matter what they are, I'm not dictating any field content, any other element within the high energy. All I'm requiring are those conditions at high energy. And they come down to some requirements on the amplitude that need to be satisfied at low energy. In particular, this is one of them. There's actually an infinite number of other bounds that we can derive because the optical theorem is not just one condition. It's an infinite number of conditions that we can impose. So that leads to an infinite number of conditions at low energy. And this one, or slightly this one, can be seen typically for non-gravitational EFTs as the requirement that the sound speed has to be subluminal at low energy or luminal, or some conditions related very strongly to that of causality.
Yeah, has this been checked when you take the mass of the particle to 0? Because there you're going to get logarithmic corrections.
So you can do,
you're going to get cuts which will merge, and you'll get logarithmic corrections.
yeah, so you can do that for spin 0, 1, a half, yeah, and that works well. In the massless limit, it's no problem for those formula. You can do it for spin massive and then take the limit of massless spin 1. And in cases where you want to see directly this correspondence, in some cases you even know what the high energy completion is, and that works very well. There's really, you can see in some cases that actually the mass itself is not particularly relevant in most of these cases, because you're working at low energy, but you don't need to, you can still work at energies higher than the mass of the particle itself. So the mass. But
it just say if I really had a massless theory, and just again in three-dimensionals where one can get in massless theories critical exponents, even you have a very different structure, and I think the s squared will be modified to a new exponent. And in 4 dimensions, I expect that to be essentially an s squared with a log of s.
Yes, that's okay. No, that's absolutely fine. The log of s is fine. That would be fine. Yeah, that is fine. I have.
All right.
Yeah, that's not going to change anything at that level. What one needs to worry is that this hasn't been proven for gravity. It hasn't been proven that for gravity you need to have that structure. I'm still going to go ahead with this because in string theory, in that limit, this condition is satisfied. So this is at fixed t, and you do have in string theory that the amplitude doesn't grow faster than s squared in a fixed t. The non-locality that arises in string theory, for instance, manifests itself when you set s and t to be a line, and then you take the large energy limit, and then you'll start seeing some elements of non-locality, but not in that limit here.
Can I rephrase Danger's question? Okay, this you are considering a particle of mass m. Okay.
Yeah.
So at low energies, well, what happens? In fact, is I think now a theorem that the particle at low energies cannot be even defined because it is completely dressed by the infrared cloud. Okay, for in QED it is photons. Here it is gravitons, and it is completely so. There are exponential of logarithms. Okay, giving you all kinds of superselection sectors, and in fact, it gives also a violation of spin statistics theorem of all things. Okay? This was proved only 2 weeks ago. Okay? There was a paper which came from Jens Mund. I think Bert Schroer and somebody else, okay? And also by Jens Mund and Pepe Gracia-Bundia. Okay? So, formulating his question, to my mind, even for massive particles, analyticity is not proved in the Manchester. This is coming from Manchester representation. That is not proved. But anyway, that's okay. But I would say that I have to agree that there is no, at low energies, this kind of representation for scattering amplitudes, when there are massless particles around, is not at all clear. Okay? There are all kinds of things going wrong there. Okay? So,
but if that bothers you, put a mass regulator.
No, that is not a massless. That is not a massless theory. The limit as mass goes to 0 is not the same as the massless theory. As the photon mass goes to 0. In fact, you cannot put a photon or a graviton mass without violating diffeomorphism.
Yeah. So I'm well aware of. I spend a lot of time thinking about the massless limit of the massive graviton. But for those cases, what I mean more by that is it doesn't need to be exactly. Even here, you don't need. I hear what you're saying, but my feeling is you can use it as a regulator. So you can use it not necessarily in the sense of changing the degrees of freedom or the dynamic structure of the particles that you have in mind, but you can use it as a regulator, and at the end of the day, take the limit where m goes to 0. So I mean, for spin one field in the massless and massive case, this has been shown to work quite well, actually. So I hear what you say, and I think some of the issues we're going to go into definitely related to what you're saying, but for massless spin one, I didn't have as much issues with it. Okay. One thing I want to do, though, before I move forward with this at least non-gravitational bounds, is to say that we can even do a little bit more than that. So there's a point where you may hit the branch cut just because you need to include loops of your low energy fields themselves before you reach the cutoff of your low energy EFT, and you need to include the microscopic states that come into play in the description of what's going on. But all the way up to the cutoff, you can actually compute the amplitude itself, and the remainder still has to be positive definite. And so you can actually do a little bit better than simply imposing the relation for the second derivative of the amplitude needing to be 0. You can include all the contribution to the imaginary part of the amplitude all the way up to some cutoff, and that has to be larger than this contribution in here, because the remainder by itself has to be positive. And so in some cases, you can, I mean, depending on how you want to read that, you can even use this as putting a bound on the cutoff of your low energy effective field theory. If this quantity is not very large, then it will tell you that your cutoff has to be needs to be quite low. Otherwise, the contribution from this branch cut is going to start dominating and taking over. And then you know that you won't be able to maintain positivity of the imaginary part of the amplitude along this axis. So in many cases, you can use this to put bounds on your on the cutoff of your low energy effective field theory, which are often stronger than what you would have expected from just naturalness arguments. Now, I hope this is going to be, this slide is hopefully a bit less contentious, because it's just as an example of what you can do with that. You can use it to constrain the dimension 8 operators that would arise beyond the standard model for the W and Z, for instance, interactions. And so we don't need to go through all of the type of operators that would come into the EFT corrections of the standard model for the W and the Z bosons, but you can imagine you have all of those operators. And by the considerations I mentioned earlier, you can see where in the region of parameter space you have to be so that the previous positivity bounds have to be satisfied, and so that you have even a chance to possibly ultimately embed this theory in a fundamental theory of everything in a consistent way. And so in green are where those positivity constraints are satisfied. So if you're outside this green region, you know that some of the assumptions that we impose on ourselves will have to be violated. And it's kind of remarkable how complementary those positivity bounds are with more experimental, more observational data. From the observational point of view, comparing with real life, there's no reason you would want to be into that green region. And so it really puts you more information in your low energy effective field theory. Now, in principle, you could start playing the same game for EFTs describing cosmology or describing dark energy, for instance. I don't want to go too much into this model per se. That's a Quartic-Hondesky model of dark energy, which happens to have some parameters, CB, CM, and CT. CT, for instance, measures the speed of gravitational waves, and the two other parameters measures the strength of the dark energy fluid interacting with gravity and with itself. All I want to say here is that you may put yourself some constraints based on observations from CMB, from various type of observations. But if you try to impose some type of positivity constraints, then you see that you actually end up being in a very different region, not very, but quite a different region of parameter space as you would have naturally expected. And so putting both of them together can really go a long way into constraining your EFTs in a much better way. Now, don't take this too seriously, or take this with a big bowl of salt, because there's too many assumptions that have been made here in the context of cosmology, which will possibly ultimately completely overrule those type of positivity constraint put on cosmology. So it's really putting some constraint, which in principle is what you would, type of things you would get, but I think it's premature to say this is precisely what you would expect.
Can you make one comment as to what the Horndesky model is? I'm not familiar with it.
Yeah, okay. It's not that I'm too attached with it, so that's the only reason I'm not commenting too much. Horndesky, if you want, it's a model of dark energy where you have a scalar field, and then he couples non-minimally with the curvature. So he has some non-canonical coupling with the Einstein tensor, for instance, which is why you start having some departure of the luminality of the speed of gravitational waves, which is embedded in this parameter CT. And then if you try to go back into a frame where matter field will couple minimally to gravity, you'll start seeing a change in the effective Newton parameter encapsulated by this dark energy scalar field. So all I wanted to think of it here is a specific model of dark energy where you have a scalar field that interacts non-trivially with gravity.
Okay, so it has a non-minimal coupling. That's one of the parameters, but you have two more.
It has self-interactions. So it has kind of minimal couplings and then some specific type of self-interactions. They are built so that it leads to a de Sitter, it leads to an acceleration of the universe, which is not relying on the potential of the scalar field, but rather on its kinetic interactions. And in the kinetic interactions between that scalar field and gravity.
Okay.
So if you want, one of the reasons originally some people in the community started being interested in those type of models is because the scale that you want to put in the game in this type of model to explain dark energy, they are of course as tuned as the cosmological constant, but because they come from interactions with self-interactions, self-derivative interactions with gravity, they are more protected into quantum corrections than just the bare cosmological constant. And so they represent some tuning of parameters which could be more stable under quantum corrections, unlike just having a bare potential for your dark energy fluid. So that's one of the original motivations in the type of these models of dark energy, or you can call it modified gravity. But then they took our lives on their own, and people now explore them in their own right as just another model of dark energy, without necessarily putting yourself in the region of parameter space where you would be technically natural. Okay, so this is just as an illustration of what, in principle, you hope you may be able to achieve. But again, those positivity priors, you can't really apply them at face value in the cosmological setup, in the gravitational setup, for many reasons. So in a non-gravitational EFT, and maybe if really my field had a mass, then we can make this connection between what happens at high energy and then positivity bounds, and then some notion of subluminality, which seems to be connected back to causality. But as soon as you add gravity in the game, all of this becomes much more murky. The connection between causality and analyticity is very non-trivial. The connection with locality is non-trivial. Whether you should impose a Fresnel band when you have gravity is very much an open question. I'm happy to be for you to debate that point, in which case I'll just say what I'm going to talk about for the rest of today is assuming the Froissart bound. And so if I see any violation of the positivity bound at low energy, then I can see that as a sign that maybe the Froissart bound was violated. But even if I assume all of those still elements at high energy, how to derive the positivity bounds and how to relate the positivity bounds to a notion of subluminality is much more subtle, as you all pointed out, in the massless limit, and particularly in the massless limit of a spin-2 field in gravitational EFTs. And so it's, of course, we know adding gravity makes everything much more subtle for an infinite number of reasons. We know gravity is non-renormalizable and things are going to be less trivial, but the reasons here why things are non-trivial is not so much because gravity is non-renormalizable. It's not because we don't know what happens at high energy for gravity. It's just within the low energy framework already, it's far less trivial for various type of reasons. Well, first there's a frame artifact, which means that the speed and the notion of speed is not invariant in the frame transformations, even though the notion of causality is. So this is just to say that an absolute notion of subluminality is meaningless when it becomes frame dependent. This is something I would say we can deal with that. That's really not an issue. I'm not even going to talk about it. It's just something you need to deal with. That's okay. As you pointed out earlier, much more problematic, and so problematic that I don't even know how to deal with, is the fact that when you have gravity in the game, you can't have something, you can't study something without affecting your space-time and effectively spontaneously breaking Poincaré invariance. And therefore, I don't quite know how to deal with the application of those requirements and what analyticity means when I don't have Minkowski anymore. And this is so difficult that I'm not going to even talk too much about it today. And that is definitely a point one needs to deal with before I can start drawing the type of picture I had before, which does, yeah, this type of picture. Okay, now yet another subtlety that arises when we're dealing with gravity is the fact that we have to deal with some notion of non-analyticity present due to the exchange of a massless spin-2 particle. And this is all the more problematic with gravity, that even if I'm not interested in scattering of gravitons per se, I may be completely uninterested by gravity, but because it is a gravitational framework, I can't prevent any massive particle to ultimately couple to gravity and have, at the end of the day, the presence of breaking of analyticity due to the exchange of gravitons, no matter what I'm interested in. So even if you're interested in standard model physics and you're just scattering fermions, whatever you're interested in, massive fields, all good. Really, if ultimately all of this is emerged in a gravitational setup, we'll always need to consider the exchange of graviton in the process. And that leads to a T-channel pole, which is just because we have a massless particle. This is the case if you have an exchange of a photon as well. But the issue with the graviton is now the residue of this pole grows like s squared, whereas if I had to deal with the photon, it would grow like s. And even though it's a breaking of analyticity for the photon, it's a breaking of analyticity for the photon, that doesn't really affect the bound I'm considering at the level of positivity bounds. These are all starting at second derivative with respect to s and higher. So for the photon, that's not an issue. Whereas for the graviton, that's precisely when it starts kicking in. And I can't simply subtract this pole because this already saturates the Froissart bound. So the remainder of the amplitude, will, if I remove that, will itself not satisfy the Froissart bound. And there's no reason this should be satisfied. Now, I'm running a bit out of time. I don't know how much time you're giving me.
Thank you. We were very relaxed with regard to time.
Okay. Okay.
We'd like to interrupt lots, so
okay.
Please not to worry about that.
Okay, so I'm going to take a little detour now to tell you why people even think about this type of things and how it could be relevant for interesting stuff, and how I think we have to be more careful. So that's in the context of the weak gravity conjecture. So so let's imagine we have a new U1 field beyond the standard model. So we have a gauge field. That's not the photon. That's another gauge field beyond the standard model. It can be the photon, but then it's a little bit trivial. And then black holes can be charged with respect to this to this gauge field, and we'll have an extremal black hole for which the charge is the same as its mass in units of m-Planck. Now, as it evaporates, you still need to have the charge less than m to avoid naked singularity, and then therefore to carry out the leftover charge, the black holes need to evaporate into a particle which has to be massive, but in such a way that the charge of this particle is at least larger than its own mass, still in units of m-Planck. So of course, if you take electromagnetism, this is trivially satisfied by the photon, and that's fine. But where the weak gravity conjecture becomes very interesting is that this has to be true for any gauge field. And so if you imagine a new U1 beyond the standard model, it tells you that you will need to have, for every new U1, some massive charged particles with charge larger than their mass. Now, if you take the EFT of this U1, it will have some operator corrections that come in. This in any EFT would expect this type of operators that come in, and they will redress the black hole mass and the black hole charge. And so in this EFT, perturbatively, the new black hole extremality condition won't be quite this one as we had it before. It'll be corrected by the parameters that come into this low energy EFT. And so I put these operators with funny coefficients in front. Hopefully it'll become obvious why I did that in a second, but for now, these are just the coefficients of this low energy EFT. Now, if it happens that the EFT itself is so that this quantity is positive, then it will always be the case that extremal black hole can evaporate as the mass decreases. This will the extremality condition will be even more easily satisfied. So in some sense, the EFT operators that come in themselves, they play the role of what would have been the particle, but you don't really need to postulate the presence of a massive charged particle with a charge larger than m. The black hole itself kind of play that role if you want. Now, what we can do is think whether the positivity bounds would impose by themselves that any EFT, any U1 EFT coupled to gravity, will automatically require this quantity to be positive. And they would just tell you that the embedding of any U1 in a consistent high energy completion forces the operators to be such that whatever you do, the extremality condition will always be satisfied, and the weak gravity conjecture will always kind of be automatically satisfied or trivially satisfied. So to see that, we can compute the two-to scattering. Here it's for photons, two-to scattering amplitude. So you may worry about the presence of a photon exchange, but this is not really the relevant part. We have some contact term coming from this term here, which is just a contact term from the photon coming into the scattering amplitude. And then we have contributions coming from the coupling between, sorry, I call it the photon here. I just mean the new U1 field and the curvature. W here is the Weyl curvature. And they contribute to the T-channel pole as expected. You have this T-channel pole as well to new contribution from the S squared. And then once again, you can find specific two-to amplitude for which you scatter specific states of the photon in such a way that what you obtain in here is precisely the same relation between the coefficients of the operators than what you had to have for the extremality condition. And so if you could argue from the positivity bounds that this quantity had to be positive, definite, then the extremality condition will always go the right way, and the weak gravity conjecture will always kind of be automatically satisfied by the black holes themselves. Now, of course, we can't quite just apply the positivity bounds by themselves, because we have this contribution which is non-analytic, and therefore spoils the applicability of spoils the assumptions that we imposed on ourselves. And so a priori, there's no reason why the remainder here has to be positive. However, there's been lots of arguments in the literature for various types of reasons that I don't want to go through. But let's assume for a second that we can put that under the carpet. And if we ignore this contribution from the T-channel pole, then we may want to be inclined in believing that the positivity bounds will impose this condition to be satisfied. And therefore, it will seem to, putting the pole issue aside, it would seem to suggest that positivity bounds tells you that the coefficients of any U1 EFT has to be such that the extremity condition has to be automatically satisfied by itself. So black holes themselves are playing the role of the charged particles with mass larger than larger than their mass. Or you can phrase it in a different way, which was beautifully phrased by Cliff Chung and Brad Rham, where if you were to think of the EFT introduced before as coming from integrating out a particle of mass m and charge q, which is why I had the specific coefficients in my EFT, then you would have the coefficient a and b to be of order 1, and that would impose that indeed the mass has to be smaller than the charge in units of Planck scales. And so that would be going towards another proof of the weak gravity conjecture. So for any low energy EFT that you come from having integrated out a massive charge, you'll see that it has to be the case that the lightest mode has to have its charge larger than its mass. The lightest massive mode, the lightest charge mode has to have its mass smaller than its charge. But you can go even further and say that you don't even need to know that there was such a thing as massive charge states. You can just have an EFT and the operators arising in the EFT automatically ensure that the black holes themselves are playing the roles of those lightest massive charge states. Okay, so this is how people have argued in the past how the positivity bounds could be used to argue for a proof, towards a proof of the weak gravity conjecture. And you will see quite a few papers arguing that these type of arguments are really going towards a proof of the weak gravity conjecture, if you can argue that this T-channel pole is not an issue and can be ignored. Now, I want to understand whether how justified this is, and really whether you can assume from the positivity bounds that you can remove that part and justify just imposing on the remainder. And for that, I'm gonna really look at the case of QED. So far, all of those arguments were really relevant, not for QED, because we know what's going on there, was more relevant for any other gauge field beyond the standard model. But now to see how applicable these type of arguments are, I'm gonna go back to the only U1 I know exists, which is that of electromagnetism, and understand what's going on in the low energy effective field theory. So now, in the only thing that I know exists, let me take a QED coupled to gravity, and I'm gonna minimally couple it to gravity. I have here the U1, the photons, and the electrons coupled to gravity. If I integrate out the electrons, I can go to the low energy Euler-Heisenberg EFT, where I see those operators coming in. But in the case of QED, I don't need to be working in the low energy EFT. I can actually be working directly, reintroducing my electrons in the game because I know what they are and I know how they contribute to the amplitude. And so if I really work at this level here, which is a consistent EFT, and we'll have a cutoff which is related to the Planck scale. So if you weren't coupling QED to gravity, then you could consider as a complete theory in itself. But as soon as you couple it to gravity, then you know that some new layers of physics will have to come in at some point. I'll include a cutoff, and that has to be somehow related to the Planck scale in a way or another. But without knowing too much what this cutoff is, I can actually compute the contribution from the electron loops within the level of the QED theory itself, all the way up to a cutoff which has to be related to the Planck scale. And if I assume that this cutoff is not dramatically low, is not of the order of the TeV or maybe 1,000 TeV, but is actually really more gravitational, then what happens is that in including this part of the branch cut, which I can compute from the loops of the electrons, this effectively will correspond to removing this part of the amplitude. The known part of the branch cut is really what leads to the positive contribution of the S square of the amplitude, and that comes from known non-gravitational contributions, which can be subtracted from the positivity bounds, and therefore I can end up with improved bounds for which just have the requirement that the remainder itself would have to be positive. But that we see is violated in QED itself. And so in QED, we know that it's not true when you have an amplitude of this form that you can simply ignore the T-channel pole and impose the positivity bounds on the remainder. And from what we discussed before, I think you probably thought that was what I'm saying here is trivial, because there always is an non-analyticity present here. And so, of course, I can't just assume it's not existing and just impose the rest on that. But it has been used as so in a lot of the literature, and the connection with the weak gravity conjecture seemed to be so close that that had motivated a lot of the assumption that you could actually have assumed C was positive. So what I'm trying to argue is, in the one case we know exists in nature, in QED, if we assume that we have a cutoff which is not dramatically low, so I'm going to assume a cutoff which is larger than this scale, then what we see explicitly is that the coefficient that comes in as positivity bounds is not positive definite. It is allowed to be slightly negative by an amount which depends precisely on the Planck scale, so that if you switch gravity effect off, this will go back to, and Planck goes to infinity, goes back to needing to be positive. But as soon as you include gravitational effects, then you need to allow for a mild level of negativity in your standard positivity bounds. And this type of relation is similar to what was obtained later by this nice paper where they try to deal with this T-channel pole instead by looking not at T0, but at finite impact parameter. Okay, so the implication within the context of the weak gravity conjecture is that it's actually not as trivial as you would have expected. And probably this is interesting. It's telling you that, yeah.
So, in your Euler-Heisenberg, I noticed you've left the E dot B term out, which I know it's a topological term if I look globally, but since the arguments are essentially local, it would seem reasonable to include you've included the Weyl theorem, but there's an epsilon with two F's.
Yes, there's an epsilon with two F's. I haven't included that. Yeah, I haven't included everything.
Would that not have a stronger effect?
No, so I'm just trying to be. I'm not including everything here, but you can include all the terms that come in, and this is the best you can do at the end of the day.
All right.
Yeah.
Okay.
Yeah,
all
yeah.
Right, thanks.
I'm sorry. I'm just being a little bit quick there. There's other operators that come in, and at the end of the day, I think it's a combination of this one and the other one. But I didn't want to include too many other terms. Yeah.
Yeah. No problem. Yeah. Thanks.
Yeah. Okay. So I think even though it's probably sounds like negative, I think that it is actually telling you that there is some real physical content in the weak gravity conjecture, and that is not simply trivially satisfied for any EFT that enjoys unitarity, causality, or the Froissart bound and Lorentz divines. Something else has to happen, because this doesn't need to be automatically positive for any such EFT. It can sometimes be negative, and if it were negative, then that would allow that would kind of violate the weak gravity conjecture. So there is some content in the weak gravity conjecture. At least it's not, positivity bounds don't, I would argue, lead to a proof that the weak gravity conjecture is always satisfied. Now, that was in the context of the weak gravity conjecture. Now, more generically, that also tells you that in terms of the connection between causality and subluminality at low energy, this is a little bit less trivial as well. And I put it here because the weak gravity conjecture, the argument that this had to be positive, was also argued on subluminality grounds. You can see that asking for the speed of photons to always be luminal or subluminal also tells you that this has to be positive. And so, but actually that's not always the case, even for, you know that photon can exhibit some level of superluminalities in a QED coupled to gravity. So just to summarize where I'm headed, in a non-gravitational EFT, at the very least, if you include, if all the modes you're considering are massive, then if you're not happy of that for photons, let's ignore them, but let me imagine a massive scalar field, then the requirement of causality and unitarity and other things tells you that the coefficient here coming in the amplitude has to be positive, and it's precisely the positivity of this coefficient that in the optical slide could be linked to the requirement of subluminality of the front velocity, of the phase velocity of the field at low energy. And you can see that in low energy scalar field theories, you can write down some operators, you can ask this condition, and when this condition is violated, you can have superluminality, and it's kind of a one-to-one correspondence between the two. So at least for massive scalar field, and even when you take the mass goes to zero limit of massive scalar field, this connection is quite nicely illustrated. Now, in non-gravitational EFTs, we already have some issues at this level. And what it means in practice is that you don't need to impose strict subluminality of the low energy phase velocity of your fields in the gravitational setup. In particular, you can allow for yourself some small amount of local superluminality, so long as sufficiently suppressed. And of course, when you decouple gravity and send the Planck scale to infinity, you should recover exact subluminality. So these effects should go to zero when the Planck scale goes to infinity. But so long as the power here of those corrections is greater than 2, you don't necessarily have a violation of causality when you have superluminalities at low energy. So in the case of QED, the QED minimally coupled to gravity, it has been shown by, for the past, I think, 40 years or so, by Drummond and Huthrell, and then by Hollowwood and Shaw, that you could have the speed of the photons being superluminal. That's really, if you look at them in the vicinity of black holes even, there's always a polarization of the speed of photons, which is superluminal. And yet you know that when you go into the high energy QED, so you bring back the effect of the electrons, you know that the phase velocity at higher frequencies becomes exactly luminal, and there's no issue with causality violation, and the front velocity is exactly luminal. So in the case of QED minimally coupled to gravity, we have some partial UV completion, and we can go to the Euler-Heisenberg EFT. We may have the impression we have some superluminalities at low energy, but we also know how to go back to the high energy and how causality is manifestly satisfied there. Now, for pure gravitational EFTs, we do not have the luxury of going back to the high energy completion and exhibiting how causality is manifested. And so what we want, what we need, is some criteria that allows us, just within the context of the low energy EFT, to establish when causality is respected, even if you may seem to perceive some element of what you typically would qualify as superluminality, because those elements may not really indicate that there is a support outside the light cone and that there is causality violation. Well, the issue with any type of EFTs So this is the EFT I'm going to be considering, and I'm going to ignore the cosmological constant because that's another one of those problems that are too hard for me to solve. But I have my EFT for gravity with these different type of operators that come in, an infinite number of one coming in, and we can have about black holes on cosmological backgrounds, on any background that spontaneously breaks Lorentz invariance. I will have the speed of gravitational waves that departs from exact luminality. So of course, the departure from luminality is extremely weak. It satisfies the LIGO bounds. That's not the issue. The issue is how to understand when you could have a small amount of superluminality, even if it's suppressed by 40 orders of magnitude, how you could have that when in principle, as soon as you have the smallest amount of low energy superluminality, you can in principle integrate it out of an infinite distance, of an infinite time, and end up with a macroscopic support outside the light cone dictated by the high energy photons, for instance. And that is an issue because then you have a support outside the light cone of what the causal structure is. And that is typically linked with some notion of a causality. So the thing is, because you are in the low energy EFT, you think you could actually integrate that over an infinite distance, over as large distances as you want, and ultimately end up with a macroscopic effect. And so understanding how this is consistent with causality, just within the setup of the low energy effective field theory, is what we want to do when we don't have the luxury to go back to the high energy completion, to ensure how causality is preserved at a high energy. So again, in the context of cosmology, I can discuss about that if you want later, but the question is a little bit better phrased if I just discussed about it in terms of scattering of gravitational waves. You can do it with photons, but let me just scatter gravitational waves around a black hole in the low energy EFT for gravity. So I have gravity with the curvature EFT corrections, and then it's going to slightly modify my black hole solutions in a way that we can keep track of. And then I compute the scattering of, let's say, low energy gravitational waves, and I compare them with my high energy gravitational waves, which don't see all of these EFT corrections. And I can compute, for instance, the phase shift. I can compute the scattering angle, and from that I can compute the time delay. So I would expect the low energy graviton to have a positive time delay as opposed to, I did it all wrong. I expect my low energy gravitons to have a time delay here, which is positive. So it takes them more time if you want, as compared to the high frequency photons or light or any other field that lives in my in the universe. And so you would expect this to be positive, otherwise you would seem to have a propagation outside the light cone as set up by the geometry of the other species. It can be the high frequency gravitational waves, or it can be the high frequency photons, etc. So it was previously argued that you could in principle have this quantity being negative so long as the whole contribution, so this whole contribution, this whole time delay has a contribution from the fact that you are in a curved geometry, you're not in flat space-time, so the contribution from the geometry itself, that already the high frequency photon C, any field that sets up the causal structure C, and then on top of that you have the corrections as seen by the low energy field, in here the low energy gravitons, because they're interacting with the other field present, and typically you expect these interactions to slow them down. But in some cases, you see that it leads to a negative time delay, so it actually seems to be speeding them up. And it was argued that this speed up is okay so long as the total time delay remains positive, but that's actually not enough, because any process which would lead to a negative time delay, or what we call a time advance, will automatically mean that the low energy, the low frequency modes are traveling faster or traveling outside the causal structure of the high frequency modes. And that is directly linked to a violation of causality. So the resolution in the causality is not in simply arguing that this quantity has to be positive. We really need to understand why this quantity here is sometimes negative. So you have a time advance, and yet this is consistent with causality at the level of the low energy EFT. So to go into the computation of this time delay, they come in from the operators of the EFT, and so they're parameterized by some of those operators. I just write them symbolically as C in here. And then, of course, they depend on the mass of the black hole. Little m here is the cutoff of the EFT. So if you want to integrate some heavy modes, that leads to those operators. And so the cutoff of the EFT is the mass of those modes. And on the impact parameter, how close you're getting from the black hole. Now, in a standard EFT, you would expect this coefficient here from the positivity bounds to be always positive definite. And so that would always lead to a positive time delay. And that would be consistent with your notion of causality. But in here, in a gravitational EFT, we've seen that this coefficient here could, because of the non-analytic structure of the graviton exchange, it can lead to a small violation of those positivity. Particularly, this can be, in principle, negative. And so it leads to a negative time delay or a time advance of the low frequency gravitational waves as compared to the high frequency photons and gravitational waves. And so we really need to understand how this is consistent with causality. Now, to understand why this is consistent, we can go back to the low energy EFT, which is only valid up to the cutoff of the low energy EFT. So this is my cutoff here. And demanding that I remain in the regime of validity tells me that all the curvature invariant has to be small, and that is okay. If I'm outside the black hole, this is going to be okay, if I'm at least sufficiently away. But it also depends on the frequency of the mode that I'm using to probing this geometry. If the frequency is too large, it's going to start back reacting on the geometry as well in a way that will start violating the validity of the EFT that I'm using to describing the trajectory of these gravitational waves. And so if K is the full momentum of the mode that I'm using to describe the geometry, at low energy, we need to have scalar invariant of this form to be suppressed compared to the cutoff of the EFT. And that tells you that if you're trying to probe this geometry with a mode of with asymptotic energy omega, you would want to say to have as large a time advance as I can, I need to ride on as much curvature as I can, because that's really what leads me to the subluminality. And so I want to go as close as possible to the black hole. I have as small impact parameter as I want. But there's a tension between enjoying as much superluminality as possible and remaining in the regime of validity of the EFT. Actually, remaining within the regime of validity of the EFT tells me that for a fixed asymptotic energy omega, there's only a finite distance away from the black hole I can allow myself to go, because if I go too close to it, and then this type of operators will go beyond the regime of validity of the EFT. And so this tension between the two is encapsulated in that relation, that for any asymptotic energy omega, I need to have an impact parameter which is sufficiently large as compared to the cutoff of the EFT, that type of relation. Now, if I plug that back into the amount of time advance, when this is negative, that we can allow for ourselves, that tells us that the time advance itself is always going to be smaller than the wavelength of the mode, the asymptotic wavelength of the mode that I'm using to probing this geometry and this level of subluminality. But if it's smaller than the wavelength, it simply tells me that the particle approximation that I use is no longer valid. This is not something which is resolvable. And there's no physical content in saying that I have a time advance if it's something which is not resolvable. So there's no real notion of superluminality. It's just using tools which are too strict to describing what's going on. Because at this level, the fact that this is smaller than the wavelength tells me that there's no real notion whether or not it's positive or negative. There's no real content in it. I can't probe such small distances with a wavelength, with a mode of that wavelength. Just to clarify, this is very different from simply saying that the amount of time, advance of time delay is below the cutoff. This is not the statement I'm making, and that would be kind of a trivial statement, but also an incorrect statement. First of all, this quantity here is not Lorentz invariant, so I can't use a cutoff to bound it. But also, nothing demands me that I'm using tools within my low energy EFT to actually probe by how much support outside the light cone I have. Nothing demands that. A priori, I could have a support outside the light cone which is smaller than the cutoff, and I'm still using high energy field to probe that and see that I generally have a physical support outside the light cone. So the resolution here is not that. It's really saying that the support that you thought you had outside the light cone is actually unresolvable because the mode that you're using to probe it will lead, the amount you have is actually smaller than the wavelengths of the mode that you're using to probe it. And so if you wanted to be more careful, you'd actually need to send a wave packet and follow it. But just the fact that it's unresolvable already tells you that it's going to be causal. Because the only reason we typically worried in computing retarded propagator perturbatively around the EFT corrections is because of secular effects, which tells you that small corrections can grow up as a function of time. And this is precisely what I was trying to say before. A priori, the smallest amount of superluminality that you can have is still problematic, even if it's infinitely suppressed, because you can have secular effect. You can integrate them out for an infinite amount of time and end up with a macroscopic effect. But in here, the very fact that we're saying that the support outside the light cone is unresolvable tells us that these secular effects are actually under control. And so you can always compute your retarded propagator perturbatively about the standard one seen by the high energy fields without the presence of these EFT corrections. And if you compute the retarded propagator at low energy perturbatively, you can't have a structure outside the light cone. You can't have a different structure for your retarded propagator because by acting differential operators on the retarded propagators as seen by the high energy field, if it's zero outside the light cone, it will remain perturbatively zero outside the light cone. And so they will be forced to sing the same retarded propagator within the level, at the level of the low energy EFT and at the level of the high energy EFT where there's no superluminality. So the unresolvability tells us that it is actually causal, it's directly related to causality. Okay, so I think I'm running way out of time. This is just my concluding slide where I motivated some notion of positivity bounds, which application can be definitely argued against in massless field theories, and I would say particularly in the presence of gravitational EFTs. Although that's precisely why they may be interesting. They may be particularly relevant for the weak gravity conjecture. And I would say the presence of small violation of those positivity bounds is precisely what tells you that the weak gravity conjecture is maybe not as trivially satisfied as you may want it to be. And it's also telling you that you can, in principle, have a small level of what you typically would qualify superluminality at low energy. I say typically qualify low energy superluminality because it's not really a superluminality. There's no propagation outside the light cone. There's no physical content in it. And yet it's just trying to dictate at face value that CS has to be smaller than 1, that would get you into trouble. You could have CS being slightly larger than 1 without being in tension with causality, because they may still lead to unresolvability support outside the light cone. Okay, I'll stop here. Sorry for taking so long.
Well, thank you very much, Claudia, for a very fascinating talk, and we're open to questions, if there are still some left. Do we have any questions? Just you've given us a very broad survey of low energy effective theories. But do you have a favorite model for what you think is going on in gravity from this point of view?
So one thing I can say is one of the direction I'm working on is, you know, you have you can go in a different direction. Let me give you a long answer. Maybe I'll go more to your point at the end of the day. You can have a more agnostic parameterization of gravitational models in that sense, where you have your operators. And what's been done a lot recently, particularly when trying to compare with gravitational waveforms, is to make this cutoff extremely low, so that those operators will start manifesting themselves in the waveform of gravitational waves, and you can start putting constraints on that. What we're seeing is that these operators will always, if you make the cutoff too low, if you try to emphasize them too much, it will always lead to resolvable amount of superluminality, and therefore that's always intention. So in most models that you want to try to probe with gravitational waveforms, for instance, you see that requiring causality is actually a very strong criteria, so much so that the chances of saying anything other than GR ultimately are going to be very weak. So that's kind of a generic answer. I can give you that. Might not be what you were quite of asking you. I mean, I went into all of this coming from massive gravity, where you have this notion of superluminality arising. And so one of the motivations was to understanding how dramatic it is in massive gravity, and how much you can allow for these superluminalities. And that is still a not completely resolved question, because it's so hard to get black hole solutions in massive gravity in the first place, and to push this type of calculations further. You'd think because you're actually dealing with a theory of massive gravity, you don't have a massless pole. So a lot of the issues related with dealing with gravity are not present in massive gravity. And so you'd think you can really go much further in imposing those positivity bounds. But it is actually not as trivial as that. So if you look at what's going on for a scalar field theory, and you simply extrapolate what you would mean for massive gravity, then you would be completely ruled out. At this level, we have sufficient positivity bounds to completely rule out massive gravity by extrapolating the low energy, the scalar field bounds onto massive gravity. But when we try to be a little bit more careful and go through what it really means at the level of a massive graviton and all the polarizations, it is never quite as simple as that. So I don't have hope, to be honest, but it's hard at the moment to completely kill the theory on those grounds.
Yeah, but it's just when I'm looking at this transparency, why have you not included an R² term or a Ricci squared?
Yeah, they're all symbolic. They're all in here.
Oh, they're just also, yeah. Okay, you're just kind of considering everything to be vile. Okay.
Yeah, but the reason it's not, I'm not putting here an R² or a Ricci squared is because I can field redefine it.
So you can
I can make a field redefinition and push it away. I can just change variable where the R² will get pushed to higher order.
Really? That's a
just a Ricci or a scalar curvature squared. I can always change my metric, and then I'll have it coming at corrections coming at high order. But there will be anything which involve pure Ricci will be field redefinable away. But yeah, anything which is pure Ricci will be field redefinable away. But here in practice, I'm going to apply this to black holes, to vacuum solutions. And so Ricci and scalar curvature will be 0. So what is really ultimately relevant is just the pure violin. And in this particular case, actually, if I'm in 4 dimensions, this is just topological as well. So the relevant corrections are coming in here. But you can do that in higher dimensions and include the contribution from that. And that has been done.
Okay. I enjoyed the talk very much. Okay, very good. Yeah.
Thank you. Thank you.
Can I ask a conceptual question? Okay. One is dealing here with quantum gravity, not classical gravity, I suppose. If it is quantum gravity, the metric is an operator in some Hilbert space. And the value but here one is ascribing classical values to a quantum operator. So that depends on evaluation on a state. So it is very confusing to me, okay, this whole procedure at a conceptual level, because I don't know what one is dealing with. Okay? Is it a quantum theory of gravity or some kind of semi-classical theory? It's not clear. I think Raphael Sorkin may make similar remarks, and also Denjo, who has worked on such problems. Okay?
Yeah. So when I'm at this stage, let's say here, when I'm at this stage, I can do all of this in flat space-time.
But so it is not quantum gravity, it is some background gravity.
No,
it's effective field theory, Bob. It's effective field theory in the sense of a Scarron model instead of QCD.
Yes, but then one is appealing to events which are happening at much higher energies and so much shorter wavelengths. Okay, so I suppose either it is a classical field theory, which one is doing some estimations, or it is a quantum theory that is getting to be constrained. So renormalizability is an issue of high energy, okay, or very short distances. Okay.
Yeah, I'm never at such high energies.
Huh?
I'm never at such high energies. I'm always at very low energies compared to that.
So it is not a theory of asymptotic completion of quantum gravity.
No. It's just a low energy EFT. There's an infinite number of operators there. I mean, if you want to write it there, it's not an ultimate theory of quantum gravity. This will break down as you go, in this case, as you go to scales related to m over q, then this theory breaks down. And that's okay. I can still define an amplitude above that. I'm simply not going to use this low energy EFT to compute it. But this is only valid well below the scale m, which is well below the Planck scale anyways.
I think you're assuming that there exists a completion which is unknown. As she began that with explaining this to us. So, but there exists some completion, and this is the low energy effective field theory, and you want to try and put constraints on it.
That does not exist. That's asking too much.
No, why did you say it doesn't exist?
Yeah.
Presumably there exists some theory of quantum gravity, and well,
but
you don't know what it is, but you would like to.
I mean, for Raphael, certainly it is not a Lagrangian field theory at all. Okay? It is something.
Well, I don't think it needs to be. But Bob, she didn't assume it was a Lagrangian field theory.
She's writing Lagrangians. For example, the top line here is a Lagrangian.
Yeah, but that's at low energy.
It's a low energy effective.
That's at low energy. At high energy, I'm not writing a Lagrangian at high energy. I don't know what's going on at high energy. I'm not computing anything at high energy. I'm certainly not using this at high energy. There may be a Lagrangian, there may not be a Lagrangian, there may be an infinite number of states, I don't know. All I know is I'm analytically continuing the amplitude to high energy, and I want it to remain unitary there. That's all I'm demanding.
Okay.
Yeah.
She,
But what comes into defining this amplitude at high energy, I don't know. I really don't know. It's certainly not going to be this. Certainly not.
you're assuming that that this effective field theory is valid up to some cutoff lambda, up to some scale lambda, and you didn't specify what
That's
lambda
right.
was. It's
But there is, if she was using Frosa bound, namely the cross section cannot grow faster
That's
than
right.
squared of
That's
S.
right. That's right. That's
That-
right. So
that
I'm using
definitely
that.
uses-
I'm using that. And if you're, I'm perfectly, I perfectly agree. If you're unhappy with that, but that's good. I need to make progress, so I'm using that. And then what you can do, if you want, is use the constraints that you have at low energy to probe how consistent that assumption was. If you end up with positivity bounds at low energy, which ultimately will be violated by nature, you see a realization of nature that doesn't satisfy those positivity bounds, then it tells you that the high energy completion has to violate something. And the Frosa bound is probably what you want to violate, because you don't want to violate causality or unitarity. So you can violate Lorentz invariance, or you can violate the Frosa bound. Yeah. Yeah, so what you can do if you want to is then be a little bit more, give a bit of some of the Frosa bound away. And you can say, well, let me not quite assume the Frosa bound. Let me allow for myself a small departure from the Frosa bound and parameterize how much this departure implies in violation of the positivity bounds at low energy.
Okay. I mean, so far, okay, just a remark. So far as my memory goes, Frosa bound comes from unitarity plus analyticity in the absence of massless particles. But here, I suppose, this is very confusing. One is putting a cutoff on the mass of the graviton, I guess. Okay. Then taking some kind of a limit. Okay. Otherwise, the Frosa bound, as proved, is not valid. So, can you hear me? Hello.
yes, we can hear you, Bob. We can hear you.
So it's not very clear. I mean, once one puts a cutoff, the theory is changed. For example, even the notion of diffeomorphism invariance, so basic to gravity, it is not clear what it means here. Okay. The moment one puts a cutoff. Okay.
So but I think in this
not very
case,
clear.
in this case, the breaking of analyticity due to the massless pole is precisely what I'm encoding, and so I'm accounting for this, and it's precisely because I have this massless pole. Here, that I can't just say that, and I'm parameterizing by how much this non-analyticity leads to a violation of this bound, and that with the arguments trying to imply, at least based on what we know, you can have that much violation on those bounds due to the non-analytic structure of the graviton. So in this case, I'm not even putting infrared cutoff on the graviton mass.
So let me just a broadcast. I don't want to comment on this line of thought because many people are working on this. I know that. Okay, there have been papers. I think Lenjo knows about. I reported it in Dublin. Okay, about this old work of Froelich, Morkel, and Strocki. Okay, and more recently, in fact, 2 weeks ago, there was a very nice paper by, I told you, Jens Bund, but Schroer and the third party, whose name I don't remember, and also by Pepe Gracia Bundia and Jens Bund, who prove quite transparently that the nature of the quantum state at low energies in QED is completely different from what we expect. The standard vacuum does not exist, and even the electron mass electron cannot be isolated because it carries a cloud, okay, of photons, and it happens that the Lorentz transformation cannot be unitarily implemented. Okay, it diverges. Okay. Furthermore, the shape of the cloud and the amount changes the mass of so the electron mass gets, and the electron spin gets not point-like. You cannot make I don't know how to make a Lagrange model of this kind, because the electron, the only thing you can say about the electron is it is a mass distribution with a lower bound. This is given by the standard electron mass. So the theory completely changes according to what they have proved. Okay. I don't know how these things fit here. And similarly, they have announced results in gravitons. I have not seen that, but this I have studied. Okay. And also the Fourier papers I have studied. And they are, I think, impeachable. Okay. They are within standard quantum field theory, and they are, there's no way you can criticize. They are mass theorems. Okay. So I have difficulties in applying mixture of two ideas to estimate what happens to quantum gravity at high energies because of the masslessness of gravitons, among other things. Just a remark, but I don't want.
Yeah. So I don't think I disagree with that. I think the fact that one is trying to push those bounds to the massless limit is definitely.
But so far as we know, in nature, the photon is massless. The limit is extremely high. Okay?
Well,
I think it's higher for the graviton, actually.
Graviton also, it must be extremely high, but I don't know. For photons, I know that the limit is very high, and you can put a limit from the known size of the Hubble constant, okay? And it is extremely small. Okay? Of course, you cannot prove it is zero because in physics we never have uncertainties. Okay?
So, but to be honest, I do agree with you. I think I'm coming from the other side that those bounds are typically assumed to be valid just in the massless limit, as if nothing funny was going on there. And while I haven't gone through all the other subtleties that you're mentioning, I entirely agree that because of the masslessness of those modes, we are seeing it is more subtle. And so we can't just jump into the same conclusions that we have derived from massive particles in the case of massless one, and even less so in the case of gravity. I agree, it's much more subtle. I mean, I guess typically I'm being argued in the other direction, where it's assumed that all of those bounds have to be satisfied, and you need to justify yourself if you violate them.
Okay.
Yeah, I definitely agree that the lesson we typically learn are in the massive case, and we kind of just push them along in the massless case, assuming everything will go through. And in the example we can look at, it's not as trivial, but that is important because we typically use those arguments to put constraints on EFTs and to conclude some element of causality without having gone through the process that we should otherwise have gone through.
Okay.
In general, it looks very difficult to work from low energies to high energies. You're working with the Wilsonian thing, a derivative expansion of your low energy effective action, and you want to try and infer things about high energy. So any guess that you make that could be helpful, I think, is reasonable to test this, to see if you can.
Yeah, I think
I agree with that.
Where I think it's going to be interesting is in application for physics beyond the standard model, where a lot of the subtleties I talked about are not present. There are the subtleties there. Of course, there are the subtleties, but they not the one I mentioned about. But in applying that to physics beyond the standard model, I think you can really try to go forward with this. Yeah, it's here. So this is just an example. Of course, you have a lot of operators, but more and more people are trying to implement those positivity bounds and all of the following ones into directly trying to gather information out of the beyond the standard model EFT.
Okay.
Thank you very much, Claudia. Unless
Let
there are
me
other
continue.
questions.
I enjoyed the talk very much. That's an excellent
Thank you for the
review.
questions. Yeah.
If there are no other questions, I will. Is there another question? There's strong interference from some speaker, which I'm not quite sure where it's going from. So I'm going to stop the recording and we can continue.